Here's a couple more examples of using cell potentials and standard reduction potentials to predict which way a reaction will go, whether or not it's a galvanic cell or an electrolytic cell. So here we have a system with chromium and cadmium-2. So what is the standard EMF of an electrochemical cell made of a cadmium electrode in 1 molar cadmium nitrate solution and a chromium electrode in a 1 molar chromium nitrate solution? So I'm going to draw this. I'm going to draw it really quick. All right, so here's my one flask here. Let's make this cadmium. And so then the cadmium ion is in here. Then we're going to connect our circuit. All right, have another beaker. In here, what are we going to put? Chromium ion, exactly. And then we need to put the chromium electrode in there, right? Whoops, connect those, bad work. All right, those guys are connected. We need our salt bridge, otherwise it's not going to go. Okay, so we have this now. Which of these is going to be the oxidation half cell? Which is going to be the reduction half cell? Well, it could go either way, right? Cadmium could be reduced. Cadmium 2 plus 2 electrons could go to cadmium solid, or cadmium solid, right, could go to cadmium 2 plus 2 electrons. It can go either way. We don't know which way the reaction is going to occur. We have to look at the reduction potentials and decide which way it's going to go. All right, so what we know is one of these guys has to be oxidized, right? One of these half reactions will be written this way, right, as a reduction potential. The oxidation potentials, right, are the reverse reactions and the opposite. So let's say bad work by me, that should be cadmium. Chromium goes to chromium 3 plus 3 electrons. That would be E-ox, and what would the sign be for that? Right, plus 0.73 volts. If dang it, C and then a D. If cadmium is oxidized to cadmium 2 plus 2 electrons, the oxidation potential will be plus 0.40 volts. All right, so which of these two wants to be reduced more? Because they're both negative, neither one really, the reduction of these is not really favorable. Push comes to shove, who will be reduced more easily? It'll be this guy with the lower magnitude negative potential. Which of these two wants to be oxidized more? The larger positive value, 0.73 volts. So chromium is going to be oxidized, and even though cadmium 2 plus doesn't really want to be reduced, he'll be reduced. So let's combine these and see. So the way I would do this, again, right, I'll write chromium goes to chromium 3 plus 3 electrons, and then E-ox, oxidation reduction potential. Oxidation potential is going to be plus 0.73 volts. If cadmium 2 plus is reduced, becomes cadmium solid, his reduction potential is still negative 0.40 volts. So if I add these up, I get a positive 0.33 volts. Right? So we figured out that the cell potential here is positive 0.33 volts, and chromium is going to be oxidized, and cadmium is going to be reduced. All right, so to do this kind of problem where you just build the cell, it's always going to be favorable. There always will be a galvanic reaction. You just have to figure out which way it's going to go based on the signs of these guys. Bad work by me, really. Let's think about another example. So predict the result when bromine is mixed with sodium chloride, sodium iodide under standard conditions. Sodium is just going to be a spectator ion, so we're going to ignore it. So this is really saying I've got chloride in there and iodide in there. All right, and so it tells me that the reduction potentials for chlorine, bromine, and iodine are these values, respectively. Let me write these reactions out. So the reduction potential, right, let's see. So Cl2 plus 2 electrons gives me 2 Cl minus. That would be the reduction reaction there. Br2, if it's reduced, is the same reaction, except I'm making bromide. And then I2 plus 2 electrons gives me, 2I minus. All right, and then the reduction potentials, I guess I'm writing them out again, are plus 1.36 volts, plus 1.70 volts, and plus 0.53 volts. All right, so these are the reduction potentials of everybody. Really, this only matters for bromine, because in our flask, what do we have? All right, we've got Br2, we've got Cl minus, and I minus. Br2 can be reduced, so this reaction is appropriate for him. Let me box him out. Okay, so bromine can be reduced, but there's no chlorine to be reduced or no iodine to be reduced. We have chloride and iodide. So really we're thinking about their reverse reactions. So let's write those. So 2Cl minus goes to Cl2 plus 2E minus, and 2I minus can be oxidized to give me I2 plus 2E minus. And so now we've got E ox equals, I didn't do the thing, that doesn't matter. Let's see, so E ox for chlorine is going to be the negative 1.36 volts, right? We changed the sign. And negative 0.53 volts. All right, so in this reaction, we've got bromine in there. It's going to try to oxidize chloride or iodide, right? It's going to be reduced, so it's the oxidizing agent. Which of these is more easily oxidized? Is it going to be chloride with an oxidation potential of negative 1.36 volts? Or is it going to be iodide with a standard oxidation potential of negative 0.53 volts? The more easily oxidized one, right? Neither one really wants to be oxidized, but this one's easier to oxidize. And so that's what's going to happen. The net reaction is going to be Br2 plus 2I minus goes to 2Br minus plus I2. And the cell potential we can calculate, right, is going to be E naught cell equals E naught red, for me, E naught ox. Reduction potential we just said is going to be, that's a reduction, so plus 1.07 volts plus negative 0.53 volts. So E naught cell is whatever that adds up to be, plus 0.54 volts. For that. So bromine's going to be reduced, iodide is going to be oxidized. Chloride will just sit there and do nothing. All right, so this reaction should become less red and become more yellow as we use up Br2 and make I2. Right, and really quick, if I use the other nomenclature, E cell, so it's going to be E cat, E naught cell minus E at the anode, right? So reduction potential stays the same. And then we take the reduction potential, but we make it a negative. So reduction potential is this minus 0.5 volts. Oh yeah, minus a positive. So then we still get plus, 0.54 volts. Again, right, so there's two equations you can use. Again, this one makes better sense to me, but people use this, so. Okay, hopefully this is thinking about reduction potentials, oxidation potentials as combined as cells, hopefully. We'll look at electrolysis, where you force the reaction to go by adding a current, right? And what we'll see is that the E cell is negative for these reactions.